This is a continuation of our notes from conic sections from last week, and how it all fits together, basically. So we did circles and we did, I believe, parabolas. And I handed out some notes for you to fill out. And I think we left off on an ellipse that has a major axis parallel to the x axis. So it's long ways like this. Okay, so here's an ellipse, and the center is always HK, and that's just how it goes. Also with circles. The distance from the center to the foci is C. So on one focus, you have H plus C because it goes to the right on the x-axis. And the other focus, you have H minus C, which goes to the left on the x-axis. So F1 and F2 don't really matter as long as you know that you're going to go to the right C and to the left C. Then there's also this distance A from the center to a vertex, the major vertex. So again, V2 and V1 don't matter as long as you know from the center to the vertex is A. And so you can go to the right A, you can go to the left A. The equation for this is x minus h squared over a squared, y minus k squared over b squared equals 1. So just like transformations that you've done before, maybe with circles, this minus h minus k is the center. That moves it around. The a and the b go underneath those terms as denominators, and it's equal to 1. And I was asked, oh, where does the b come from? The b is half the length of the minor axis. So from the center straight up is b. It's straight down this way is b. Note, because A is the length of the major axis, it is always longer than B. So A is always longer than B. If they were equal, it would just be a circle. You would have no foci. You would just have a whole bunch of vertices. So that's a circle when A equals B. Also, we noted B squared equals A squared minus C squared. Why? Well, it is the Pythagorean theorem. So take a look at this ellipse. And remember that the definition is the distance from F1 to any point and F2 to any point. When you add it together, it's the constant 2a. Well, why is it 2a? Think about a pencil moving around this ellipse, okay? And this string stays a constant length. Let's say this F1 to P and F2 to P is a constant length. And you can move this pencil anywhere you want, but it's tied to F1 and F2. It's not a rubber band, it's a string, so it always stays the same length. Now, F2 to V1, if you put that point P on V1 right here, F2 to V1 is A plus C because you're going this distance C and then you're going this distance A. And then this little bit, F1 to V1, is A minus C. So it's this little bit right here. And if you add those two things together, like the definition says, then the C's cancel out and it's 2A. The algebraic notation is this. This means plug it into the distance formula and you should get 2A. So now, instead of putting P on the vertex, let's put it up here where B is, and we're going to call that point Z. That gives us two right triangles that are equal. So if I use the Pythagorean theorem, c squared plus b squared equals h squared, h being the hypotenuse here. Which implies, of course, if I subtract c squared from both sides, I get b squared equals h squared minus c squared. Which, okay, now how does the hypotenuse equal a? Well, if you go from F2 to Z and then F1 to Z, they're obviously equal because we have two equal right triangles. So by definition, if I take a look at this, F1 to P, F2 to P equals 2A, but these two are equal, so I can substitute in f2 to z. f2 to z equals 2a. Well, then that implies that one of them is just equal to a, and we said f2 to z is equal to the hypotenuse. So there you go. That's why b squared equals a squared minus c squared. You don't really have to memorize that. I just wanted to point out why that was. Okay, the ellipse with the major axis parallel to the y-axis. So it's going to look something like this. It's going to be taller than it is wider. Notice that A is still longer than B. However, A is now parallel to the y-axis and B is parallel to the x-axis. And we still have C here from the center to the focus, which is also parallel to the y-axis. The center, as always, HK. Now the foci, instead of adding and subtracting C to the x value, we add it and subtract it to the y value. And then same thing with the vertex. We're going to add A to the y value and subtract a from the y value. Now the equation changes. You still have x minus h squared plus y minus k squared, but a squared is underneath the y term and b squared is in the denominator of the x term. So the larger number is underneath whichever one it's going to be parallel to. So if the larger number's in the x term, then it's going to be parallel to the x-axis. If the larger number is under the y term, it's going to be parallel to the y-axis. So you might want to write this down on your notes, the foci, the vertex, the equation, and all that. Okay, the hyperbola. It's kind of cool looking. The hyperbola is if you flip an ellipse inside out, if you want to think of it that way. It goes on forever in both directions. The definition of a hyperbola is all points, p of x, such that the distance between f1 and p and f2, they subtract to some constant. And we say plus or minus 2a because it depends on whether f1 is on the left or right and f2 is on the left or right. So just know when you subtract the two distances, you're going to get either a positive 2a or a negative 2a. The center, again, as always, is HK. But notice that the distance from the center to the focus is longer than the center to the vertex because it's that ellipse kind of flipped inside out. The foci are on the other side. So C is going to be greater than A on this, unlike the ellipse. So here's C, longer than A, because the focus is on the outsides of the vertices, if that makes sense. Also different than the ellipse. The ellipse was b squared equals a squared minus c squared, but the hyperbola is b squared equals c squared minus a squared. So write that down on your paper in your notes. The foci are the same as the ellipse. You're going to add and subtract c to get to the foci. The vertices, you're going to add and subtract a. And then here's the equation. What else about the hyperbola? Well, where's b? B is right here. Like I said, it's an ellipse flipped inside out. You take the foci and you move them outside the vertices and you have the hyperbola. So B is right about here. There are 2 points. It's plus B on the y-axis and minus B on the y-axis. So together with the two vertices, it makes a rectangle. Sorry, it didn't touch V1, but that rectangle is supposed to touch V1 right there. And this rectangle helps graph the hyperbola's asymptotes. If you remember, asymptote is a imaginary line that a graph does not cross. It just gets infinitely close to it. So those asymptotes go through the corners of the rectangle and the center of the hyperbola, and they go on forever just like the hyperbola. These asymptotes, since they go through the center and they have the slope of b over a, because remember the change in y over the change in x is a slope. So from here to here, like that, that is your slope. And so the equation of the asymptote is point slope form right here. Y minus k equals plus or minus b over a x minus h. Plus or minus, of course, because you have two directions that you go for the asymptotes. You also have, just like an ellipse, an hyperbola parallel to the y-axis, center, hk as always. Foci are now added and subtracted to the y value of the center because it's going parallel to the y-axis. The vertex, add and subtract from the y value. B squared, again, equals c squared minus a squared. Now, look at the equation and how it's different than the hyperbola that's parallel to the x-axis. The a squared is still on the left and the b squared is still on the right. However, the y minus k is the positive term and the x minus h is the negative term. So instead of moving the bigger number, I guess, under the other xy or whatever we did for the ellipse, it's more common to put the y value first with the a squared under it as the positive one if it's parallel to the y-axis, and vice versa. So that's just a little bit different how it looks than the ellipse. The asymptotes are the same. They go through this rectangle that you make with a and b, but now the slope changes because it's the change in y is a over the change in x is b. So the asymptotes are y minus k equals plus or minus ab times x over or x minus h. Okay, that's all I have.